Okay, folks, let's get moving. A couple of announcements. One is the full reading list is finally up. Apologies for that. So that should be accessible through the hub. In fact, it is accessible through the hub because that is the hub. Couple of points to make. There's a number of articles on there. There's a bunch of things which, this is not compulsory reading. Pretty much everything in there will be pertinent to what we're talking about, will be relevant and could be helpful in the exam, but it's not compulsory reading other than the sort of core texts. Speaking for my stuff, that one, which is Arno and my book, the lecture that I did last time is mostly from chapter 2 in there. And a little bit of what I do today is in chapter 2, and chapter 5 will be the most directly relevant for us. But there are a number of other books that are useful to go to. If you are interested, as indeed one should be, in general aspects of rationality and thinking and deciding and judgment and decision making, then you could do a lot worse than go to Jonathan Barron's book, 2006, which is probably one of the most sort of seminal, widely ranging texts in this area. Another one that's more recent is this one by Michelle Baddeley, which actually I have not used as a textwork before, but have started going through this in the last year. And this is really good. I think chapters in here, particularly chapters 6 and 7 of Michelle's book, are very well worth reading, chapter 6, much more on the heuristics and biases stuff that we discussed last time, and chapter 7, more on expected utility and cumulative prospect theory and the formal frameworks thereof. Today is very much the kind of heavy lifting day in terms of getting through the formal models that we need to in order to start applying aspects of behavioral science into quantitative and mathematical finance, into portfolio optimization. So there's quite a lot today of equations, charts, etc. Most of the content here is replicated at least to some degree of detail in chapter 5 in our book, but there are bits and pieces that I'm going to go a little bit deeper today. I'm going to touch on aspects that aren't in the text, and also let's just see, any questions that you have on quite happy to go off on the odd deviation. I'm going to try today, we'll do 2 breaks instead of just one in the middle, so we'll take a break after an hour and another one after 2 hours, just to give everyone the opportunity to reset brains in a very long lecture. Any questions from you guys before I kick off? Anything from last time? Any questions are welcome, except for questions about the coursework, which I have no idea about whatsoever. Okay, so we left off last time having arrived at expected utility theory. Expected utility theory is the normative model that really underpins all of economic analysis. And it might sound funny for me to stand here as a behavioral person and focus a lot on expected utility theory. But the key word here is that one, normative. Normative, in terms of a model, means a model of how people should go about doing things. And we need to contrast normative models with descriptive models. And a descriptive model, of course, is a model that describes how people actually go about doing things. And this distinction, I think, has a tension that's at the heart of everything we do. As humans, we behave in a certain way, and a certain subset of academics want to describe how humans behave, so we want descriptive models. We want to understand the heuristics, we want to understand the biases, we want to understand behavior, and we'd like to have a model that describes it. Great. On the other hand, if we are trying to optimize a portfolio for someone, we are trying to figure out what is the best way of doing something, rather than to describe what people actually do, because what people actually do is very seldom the optimal rational thing. So even if you're taking a behavioral perspective on things, the normative models really are the touchstone against which you should judge everything else. So expected utility theory is, in economics, that touchstone. It has an enormous amount of benefits, and it has a certain number of flaws. I'm kind of assuming that most of you, if not all of you, have come across expected utility theory and its derivations and proofs at some point before. I'm not going to go through the proofs of how we get there, but it is important for you to understand what expected utility theory is and what it isn't. So what it is actually pretty simple. Expected utility theory is what we call a representation theorem, which is to say, if we make certain assumptions about how people's choices play out, about how people's preferences play out, and those assumptions are axioms of rationality, then expected utility theory says that we can represent someone's choice ordering by using a utility function that ascribes a particular value to every possible outcome in their choice set. So explicitly it says, if I have a whole bunch of different outcomes, xi, then as long as people's choices obey these axioms, and those axioms are things like, I can evaluate options independently. The set of options in the choice set doesn't influence the value I place on any one option. I can value the options one by one by one and look at them independently, and my utility from that option will be the same even when I put a lot of other things next to it. So it assumes there's an independent value to every option. It assumes transitivity, which quite simply put says if I prefer A to B and I prefer B to C, that I must prefer A to C. I can't suddenly go, well, I like B better than A, I like C better than B, and by the way, I like A better than C. So transitivity, fairly fundamental axiom of rationality. Completeness. For every choice in my choice set, I either prefer A to B, or I prefer B to A, or I am indifferent between them, which basically is just saying that I am capable of making a choice, or I'm capable of evaluating two options, every set of two options next to each other. And continuity, which says if I prefer A to B to C, then I can match the utility of B by a blend of the utility of A and the utility of C. So I can blend these things, and it means that basically I don't have discontinuous jumps in the utility I ascribe to my choices. Now, these axioms are all fairly fundamental, and expected utility theory says if they hold, then there is some function that ascribes a number to every outcome in my choice set, such that when I calculate the expected utility of each option, my preference ordering over choices is exactly replicated by the rank ordering of the expected utility of each of those numbers. Okay? So that representation theorem doesn't actually tell me anything about what that function is. It doesn't make assumptions about the function. It doesn't tell me that I should do it that way. Well, it tells me that I should do it that way, but only if my preferences are well ordered. Now, what utility theory in its basic form does not assume, it does not assume anything about that function, it does not assume risk aversion, it does not assume diminishing marginal returns. These are all things that we place, and also it does not assume that x is a numerical number. It does not require the outcomes to be a money value. That outcome could be some state of the world with emotions attached to it, with fuzzy things that I cannot actually write down. When we start applying it to finance, we make further simplifying assumptions. And those assumptions are, well, I'm going to ascribe utility to a number. I'm going to be able to ascribe utility to a pound outcome or a dollar outcome. We then say, because I have a number here, I can actually create a function that has a mathematical form that maps one to the other. So I can start to say, is this a power function? Is it an exponential function? Is it a parabolic function, etc.? And then in economic use, typically what we will do is we will make, firstly, X wealth levels. We will say my utility is a function of how wealthy I am. We will say that I get more utility if I am wealthier and less utility if I am less wealthy. So people like more to less. There's often a monotonicity assumption in there. And then we say, actually, I am risk averse. So in a lot of practices, we assume that this utility function is a concave function of wealth. So I can say there are diminishing marginal returns. I get more pleasure from each unit of wealth, but it comes in a decreasing way. And I get a function that looks like this. And that is what is used in an awful lot of economic analysis. It's used in what's used in a lot of financial analysis. But it is important to realize that much of this is additional weight, additional assumptions that have been imposed on expected utility theory, which is a much broader, more general theory. If I have a concave function, what it means is that the utility, if I have a 50-50 gamble between wealth level 1 and wealth level 2, it says I would much rather have the 50-50 value, the value in the middle. I'd rather have that for certain, than play the gamble of 50-50. So, for example, if wealth level 1 is $50,000, wealth level 2 is $100,000, the 50-50, the expected value in the middle is $75,000. If I have a concave utility function, it says if I had $75,000 for certain, my utility would be up here. But if I average the utility of 50,000 and the utility of 100,000, it comes out lower. What that essentially means is I'm risk averse. I will avoid playing gambles, and I will accept a lower certainty equivalent on that gamble. Now, that concavity is actually a very strong assumption that a lot of Kahneman and Tversky's work challenges. It says that people simply do not seem to behave that way, and I will get onto that very shortly. But one of the most important assumptions of expected utility theory is this notion of independence, which basically says when I have a bunch of options, my expected utility is equal to let's say x1, p1, x2 times probability of 2, x3 times the probability of 3, etc., etc. It says that I can evaluate each of these with no reference to the others. And that is what tends to fail, because we saw last time that when I start putting different options on the table, it will influence the utility of the options I've already got on the table. If I'm choosing between a small and a medium coffee, I might have a certain preference for a medium coffee. If I then add a large coffee, it might change my preferences for the small and the medium. It might change my weight. And that failure of expected utility theory is one that undermines an awful lot of rational choice and decision science. Now, why is that the case? Well, expected utility theory implies this. It implies the sure thing principle. And the sure thing principle says that if something is the same in every possible state of the world, if the outcome is the same in every possible state of the world, then the probability of that state of the world is irrelevant to me. So here we have, for example, two investments, and imagine there are three states of the market. The market can either be up, it can be flat, or it can be down. Investment one, if the markets are up, I get £1,000. If it's level, I get £500, and if it's down, I lose £100. Investment two flips around. Actually, investment two, I do better if the market stays flat. If the market goes up, I still do okay, but not as well. And if the market's down, I also lose £100. What the sure thing principle says is that this minus 100 is irrelevant to the decision, because it doesn't matter whether I choose investment one or investment two. If the market goes down, I get the same outcome. It's a sure thing. I get the same outcome regardless of which investment I choose. So if I'm choosing, do I want investment one or investment two, what I should do, what I should do is just ignore what happens in the down state of the world. And I simply go, actually, what is relevant to me is simply, do I think the probability of up outweighs the probability of level? If I think yes, if I think up's more likely, I go for investment one. If I think level is more likely, I go for investment two. How likely I think the down scenario is utterly irrelevant to the choice. And that is implicit in this separation thing here. And that's what tends to fail. Now, very shortly after von Neumann Morgenstern published The Theory of Games and Economic Behavior in 1947, which was the first exposition of expected utility theory, very quickly after that, people started coming up with counterexamples. And the first was Allais, who was a French econometrician. Well, he was a French economist. Turns out he also actually wrote comments on Einstein's theory of relativity as a physicist, so he was one of these multidisciplinary individuals. But he started coming out with counterexamples, and he said, if I give these examples to people, what they choose does not obey that axiom. It does not obey the separation of alternatives. And this was one of his most famous ones. There are a number of different Allais paradoxes. It's worth going and sort of spending a bit of time studying them. It's not relevant for us to understand all of the ways in which expected utility theory can fail, but it's important to understand some of them, and this is one example I'm going to give you that I think it's worth getting inside. If people are given a choice between option one, where you get £1,000 for certain, doesn't matter, you've got it, or do you want to choose option two, where you get £1,000 with an 89% probability, there's a 10% chance you get £5,000, and there's a 1% chance that you end up with nothing. Now, what Allais discovered is when he went to people, and these weren't stupid people, he actually gave these examples to Savage, who is one of the, who's the statistician who developed expected utility theory into subjective and away from objective probabilities. He found that most people choose option one here. And they go, well, yeah, of course I'd like to have the chance of getting £5,000, but what I really don't want is that, even though it's small, I don't want that chance of getting zero. I'd rather have £1,000 for certain. Allais then said, well, what if I give this same set of people a different choice? And here you get £1,000 with 11% probability and 0% with 89, or £5,000 with 10% probability and 90% chance that you get zero. What he found here is that most people went for option four. And I must say, I find that quite intuitive too, because look, there's only a 1% difference here, but I get 5,000 here and I get 1,000 here. And the increasing chance of me getting zero is only 1% more. And the increase of a percentage chance from 89% to 90% doesn't seem that important in the bigger picture. Now, why does this particular choice pattern fail expected utility theory? Imagine I could reconfigure this choice, and I had a big ball, a big container of balls. And those balls were numbered from 1 to 100. You're going to pick one of them out. So I could put on every one of those balls, in each of these choices, I could put the number that you would win. So in option one, every ball has £1,000 written on it, and I dip it in, and I pull it out, and hey presto, I've got £1,000, fine. Here, balls 1 to 89 have £1,000, balls 90 to 99 have £5,000 written on them, and that ball number 100 has 0 written on it, and that's my gamble. So all I'm doing is I'm taking these probabilities, these odds, and turning them into something physical. Now, if I do that, what we see is, here's option one, £1,000 regardless of the ball numbers. Option two, I've got one ball that has a chance of 0, 10 balls with a chance of 5,000, and a bunch of 1,000, etc. Option three, option four, same. Now, if my choice is between option one and option two, it does not matter to me what happens if I pick balls 12 to 100, because balls 12 to 100 are exactly the same value regardless of which I choose. So my choice should only depend on my preferences for this subset of the gamble. If I choose option 3 versus option 4, the same thing happens. I get 0 in both cases if balls 12 to 100 come up. So it is irrelevant to my choice between 3 and 4. Once I cut out these sure things here, what you get in the rest is you see that these two superficially very different choices under expected utility theory are exactly the same choice. There is absolutely no way that I should be able to choose option 1 over option 2 and yet choose option 4 over option 3 in expected utility theory. And this is because it fails this separability axiom. The fact that I add in these irrelevant things actually changes my preferences for these previous outcomes. So expected utility theory fails in some very fundamental ways. And I mean, LA was going around conferences giving these choices to economists, watching them say, you know, what would you choose? And they said, I choose this and that. And then in a, I presume, rather annoying fashion, proceeded to point out to them that they were actually, in fact, being irrational. And what he found is that a lot of people got quite aggrieved by this because although they could see that they were being irrational, it didn't feel irrational. They still went back and said, I would still choose that rather than that. So Kahneman and Tversky they spent about a decade looking at a whole range of choice anomalies, these paradoxes that did not obey expected utility theory. It is well worth reading on this one, not Thinking Fast and Slow, although that is good too. I'm thinking of the Michael Lewis one, The Undoing Project, where he describes their interaction as a team over this time. What they ended up with was a model of choice that was descriptive. It included in it, if you used this model, which is prospect theory in its initial variation in 1979, or cumulative prospect theory in 1992, this model was a way of loosening this assumption of separability and had a lot of features in it that seemed to describe patterns of choice that we actually observe when we make people take these gambles. Now, I have to say, it doesn't explain every pattern of choice. There's a great, a lot of people think, oh, prospect theory solves it, that's how people decide. This is not true. Prospect theory, firstly, is not a dynamic model. It is a completely static model. It has at the heart of it this reference point, but there is no model of how that reference point develops. It's no model of how that reference point is set. So it's a model that is specific only to a choice set at a point in time. And there have been a whole sub-literature that is extremely arcane, and I don't recommend you go and look at it, but if you want to, Michael Birnbaum is an American professor who has, for the last 20 years, been crafting these very complex choice experiments that demonstrate exactly where and how cumulative prospect theory fails as a descriptive model. So it's not a perfect model, but what they did is in a single model, they managed to encapsulate a vast proportion of, encapsulate explanations for a vast proportion of these choice anomalies in this single model. And it looks like this. Well, part of it looks like this. The first thing is, they said, okay, we observe that sometimes people are risk-seeking and sometimes they are risk-averse. So the function we use, and they call this a value function rather than a utility function for some quite good reasons, but because it's not in utility theory, we won't call it a utility function. But the function that ascribes a particular psychological value to every outcome has portions on it that indicate risk aversion and portions on it that indicate risk-seeking behavior, convex and concave portions. The bit that divides the two is this reference point. And this is absolutely fundamental to their model because they said, actually, this assumption that people care about wealth levels, that wealth levels is what I ascribe utility to, doesn't seem to hold water. Because if you recall, in the last lecture, I gave you that example of a stock. You'd had $6,000 of a stock that had gone bankrupt. And if I portrayed the choices to you one way, people tend to be risk-seeking. If I portray the choices to another way, people tend to be risk-averse. This notion that I can flip people between risk-seeking behavior and risk-averse behavior by changing the wording of a question is what I'm implicitly doing is I'm changing where you position your reference point. Your reference point is either I assume I've still got the money and I'm losing, in which case people are risk-seeking, or you say, you position the reference point to say, imagine you've already lost it, how much can you get back? And for exactly the same monetary outcomes, you can flip people around. So this, what they did is to say, forget about wealth levels. What people ascribe psychological value to much more is changes in my wealth from my current position. So imagine you are a millionaire, you have £1 million, and I went to you and I said, how would you evaluate a gamble with a flip of a coin, and you will either win £10 or lose £10. Now, the classical approach is go, well, what you're doing in your mind, if you're thinking about this in the expected utility lens, is I'm trying to evaluate the prospect that says I have a 50% chance of £1,010,000 and a 50% chance of 999,995, or sorry, 990, right? That doesn't seem intuitive to us. When we think about a gamble of plus or minus 10, we're thinking about a gamble of plus or minus 10, not 1,010,000 and 990,000, etc. So that single distinction, that what people care about is changes from their current state rather than the overall state itself, lets a huge amount of psychology into a decision model that was not there before. So prospect theory said, let's change the value function. Instead of being on wealth, we will have this as deviations from wealth, gains and losses. That allows us to ascribe a concave portion. People are risk averse. They tend to be risk averse when it comes to gains. They tend to be risk seeking when it comes to losses. And people seem to very rapidly lose utility as they cross the boundary from plus £1 to minus £1. So this is where we get loss aversion. Loss aversion, they built into their function, there is a kink in that function. There is a discontinuous, well, it's not discontinuous, but it's not a smooth function. At 0, it flips. So where you place the reference point makes a huge difference to how people evaluate something, because as you cross from gains to losses, people will give up an awful lot of traditional expected utility in order to not experience those small gains, those small losses. So